Hello again. We're going to start the afternoon session, and we're going to have this afternoon the participation of Noelia Sanchez, the roundtable, and the working group presentations. So let us start with the class from Noelia Sanchez. Noelia is an aerospace engineer working at Tecnoldeimos in the field of mission analysis and space debris. Regarding space debris activities, she has focused on conjunction avoidance research and surveillance and tracking, SST systems. In this field, she has developed operational systems for collision risk evaluation and object cataloging software solutions. She has worked on the analysis and definition of the future ESA SST system. And in the mission analysis activities, she has focused on orbit determination activities, working on the evaluation of capabilities for asteroid deflection estimation. Noelia is currently the head of the Space Situational Awareness Division at Tecnoldeimos.
Thanks a lot, Juan Luis. Can you hear me well with the microphone? Yeah? My talk is, I think, a bit different to what we have seen this morning. We have seen a lot on technologies, very challenging technologies on deflection, attitude estimation. In all these presentations, there has been one thing that is given as granted, is the existence of a catalog. We know there are several objects in space. There is a catalog of objects in space. We know their orbits. And that's the way we know how the space environment is. So my talk is focused on how we construct, how we build this catalog. So I will talk from observations to cataloging. This is a bit the agenda, the contents I will review. I promised myself to make it very light. I know it's the hour after lunch. So no equations, no complex theoretical background, just a light review of the main techniques. Of course, if there are some questions, we can at least try to address them. So first we will do a very small review of which are the objectives of cataloging. You know all which are they, which are the current catalogs we manage, and which are the main techniques we need to use. Regarding the techniques, I will review some of them, and they are grouped in two main parts. The first one is how we observe the objects, because this morning we have been talking about radar, telescopes, but there's no explanation up to now. Why are we using both systems? There are technical reasons for doing so. And the other part is how we build the catalog, how we compute the orbits once we have observed the objects. So which are the objectives of having a catalog? As we all know, is we need to know where the objects are because they pose a risk. We need to monitor the objects. If we want to compute the collision risk in order to make our operations in space safer, we need to know where their objects are and to be able to propagate them. We also need to know if they are going to re-enter, but we also need to monitor the activities in space. For example, just to check if the other operators are compliant with the guidelines. So there are many objectives of having the objects cataloged. As Holger has mentioned this morning, we are not only interested on having a catalog. There are many techniques to model the space population, and we need to differentiate between modeling and cataloging. For modeling, as he mentioned this morning, it's enough if I count the objects crossing the field of view of my sensor, because I want to know how many objects and roughly in which orbital regimes they are. But for cataloging, we really need to identify every single piece orbiting in space. And identify means to know accurately which is the orbit and even who is the originator of that object. That's the main difference. There is a huge difference in the number of objects that are modeled. There are something like 600,000 objects in the models, 600,000 objects larger than 1 centimeter. We cannot observe objects larger than 1 centimeter. We are happy if we can observe objects larger than 10 centimeters. There are 15,000. It's not that small if you consider that you need to know exactly, or the most accurate as possible, where the objects are. This plot below, I think we have already seen this morning. It provides the evolution of the number of objects along the space history, let's say. It comes from ESA Discos database. Just to draw your attention on the number of payloads, as Holger mentioned this morning, is very low. The rest of the objects in space are space debris, or objects that are not useful any longer. So we cannot rely on the operators of those objects to let us know where the objects are. For the others, we need to observe them and try to compute their orbits. This summary of technologies we use for observing objects in space and cataloging objects in space is also a way of telling the world that this is also difficult. I'm really used to see people laughing when I say, what are you doing? I do space debris. Wow, space debris, what's that? And people imagine that we are doing things like that. There are many comics about space debris engineers. But for me, the space debris issue, the observation and the cataloging, is not this, it's that. There is a need of a very good, of course, as in all the engineers, mathematical and physical background. We need to propagate orbits. We need to take into account the orbital uncertainty of those objects. And that's an issue which is very much important in this field, because we do not have collaborative objects. So really the uncertainty plays a major role. We also consider the measurement techniques, and there are plenty of measurement possibilities with their advantages and their drawbacks. And they have to be known, because if we do not know the limitation of the different sensors, we cannot consider, or we cannot properly consider, which is the best way to observe the objects, which are the limitation of our catalogs. The limitation of our catalogs will constrain our capability to avoid the risk. Of course, we always handle with orbit determination activities. The orbit estimations, just by computing using the orbits, the observations to compute the orbits. But we handle also with mission design. We have seen this morning there are plenty of issues about mission design for active debris removal missions, but also for re-entry, controlled re-entry. We can handle, we need to handle with mission design for collision avoidance, optimum collision avoidance. So it's really a compendium of all the techniques that are normally used in space. There's nothing to do with some comics about that. And there is one thing I like a lot about this cataloging stuff, is that there's always something that requires a bit of imagination, something that you didn't expect, some object that should be there but it's not there, why it's not there, or why this object is moving much faster than I expected. There are a lot of issues that are not that issues you expect before. So we'll review a bit all these techniques. Of course, very lightly, as I said before. Before going to the techniques, I have just put a summary of which are the cataloging activities that are done at this moment. There is a de facto catalog, international catalog, which is the one provided by the Americans. They compute accurate orbits, but they do not publish the absolutely accurate orbits, but the two-line elements. Most of you have already handled with that. They are mean elements. At least we have the mean elements, but they cannot be used for everything. We know which are the limitations. For example, nobody is doing collision avoidance with a two-line element catalog because we need more accurate orbits. But at least it can give us a good idea of where the objects are, which are the orbital regimes that are more populated. There are some other efforts at the national level. For example, France maintains a catalog, not for all objects, limited to bigger objects in LEO. There is also a plan between different nations or managed by the European Commission to build an European system. There is, of course, the ESA initiative to set up the space surveillance and tracking system. And there are also some other initiatives run by amateurs or university teams like ISON. They have a huge number of telescopes to create a catalog in the high orbital regime. Also some private initiatives, which are very popular in the last, I would say, weeks. But this is quite expensive. The number of sensors you required is large. The operations are difficult. So in the past, we have seen a lot of testing campaigns, experimental campaigns. But having a continuous cataloging system is not that normal. As far as possible, I have tried to put some plots or numbers coming from real operations to show that this is done. Unfortunately, as I mentioned, it's not that easy to have real numbers, real cases. Most of people are working with simulation. So simulation modeling is also an important issue within this field. Just a summary of the number of objects. This morning we have been talking about criticality, the LEO problem. We all know that most of the problem about collision in space is in LEO. The number of objects we have is very much larger in the lower altitudes. This is apogee height up to 2,000 kilometers, whereas this plot runs out up to 40,000. The number of GEO objects, this is the GEO ring, it's about 800, while the number of objects in LEO is much, much larger. So the problem is in LEO, but we should not forget about GEO. GEO has a special condition which makes difficult to observe, and makes that most of the operators are, as you know, concentrated in the very same orbit. So it makes very difficult to differentiate when I observe one object, to assign to which object that observation belongs to. MEO, region, GPS satellites, it's not that bad, but still it's worth it to make an effort to catalog them. So, as I mentioned before, we split the presentation between the observation techniques and the actual cataloging techniques, what we need for cataloging. For the sensors, we have to differentiate between how we observe when we want to model and how we observe when we want to catalog. For modeling, this morning we have seen very nice pictures about in situ measurements. I send something to space, or even I retrieve the panels from shuttle, and I can see the impacts. I can use the counts of the impacts to model how many objects I have in space, but I cannot compute an orbit from that. That's a technique I can use for modeling, but never for cataloging. There are some sensors, like the radar. Holger again mentioned this morning the beam park experiments. We use a radar, we just look into the sky and count the number of objects. The same radar, the same sensor type can be used for cataloging, but the observation mode is a little bit different. For cataloging, we use radar, telescopes, which can be on ground or even space-based. This morning has been some question about space-based sensors. They are used for cataloging purposes. And there are other techniques like laser ranging systems, which are used also for computing the orbits, but can be used for computing the altitude. Why are we using radar and optical sensors? Radar are very much useful for the lower part of the orbital regimes. They can, let's say, safely cover the LEO region. Of course, we cannot observe the very tiny objects. Depending on the sensor, depending on the radar, we can have 10 centimeters, 5 centimeters objects in the lower part of LEO, and of course, a little bit larger objects in the upper part of LEO. But we cannot use radars for GEO. Not absolutely, it's not possible. But there we have the telescopes. One can think, okay, if telescopes can reach up to GEO, why are not using them for LEO? The point is that we need that the object is illuminated. And a very low object is very bad illuminated, or it's only illuminated under very constrained conditions, which make very difficult to maintain a catalog. As I said before, we can also use these space-based sensors. We are going to have a brief description of what we can obtain from them. Space-based telescopes, for example, can solve two problems encountered with the ground-based telescopes. The first one is that on ground, if there are clouds over our station, we cannot observe. If we put a telescope, a sensor, on a platform, on a satellite, there will be no clouds for sure. So that helps. And additionally, we can get closer to the orbit regime we want to observe. So we theoretically could observe smaller objects. We will see a bit afterwards if that helps or not. This is a plot I like a lot to explain why we do not use telescopes in the lower part, or we do not use radar in the upper part. The graph provides the diameter of the objects we are observing and the altitude of the object, the orbital regime. There is a limit, about 5,000 kilometers, where the radar are not effective at all. And above that limit, we need to observe optical systems. The different lines, the different curves correspond to different sensor types. We can move a bit this curve, which limits the detected objects and the undetected objects. We can push a bit this limit, but we cannot push it completely. We can get this limit a little bit up, but we will never observe radar with a radar at the GEO part. This is simulations results for an architecture of an SST system, and I have put in blue the objects that are observed by radar. And you can see these are only the LEO objects. As always, red is bad. The red points are those objects that are not observed. And we can definitely see that the higher the orbit is and the smaller the object is, the more difficult to be observed. Optical can make the work in the upper part, but cannot go that small that we do for the radar. So normally in GEO, we can observe objects down to 50 centimeters. But that makes the deal, because the catastrophic collision, as Holger also mentioned this morning, the most constraining issue for defining a catalog system is how accurate you want to know the orbits and how small is the size of the object you want to detect. Normally, these two conditions are driven by the catastrophic collision. And in GEO, we can safely say that if you catalog 50 centimeter objects, you are cataloging most of the catastrophic collision. On the contrary, for LEO, you need to catalog about 5 centimeter objects because the higher relative speed to be sure that all possible catastrophic collisions can be estimated. The reason why we cannot go that high with the radar is because in the only one equation in the talk. The link budget, the signal-to-noise ratio, depends on the fourth power of the range between the object and the station. as he mentioned this morning, we need to send a signal and receive it back. So it goes twice, and we lose a lot of signal. That doesn't mean that you can define a perfect limit. Okay, if the object is 10 centimeters, I will observe it. If the object is 5 centimeters, I will not observe it. That's not the case. Of course, we always deal with probability of detection. This is what I have tried to plot here. Depending on the altitude of the range, the distance between the station and the object, and the size of the object, we have a probability of detection. For sure, very large objects at low altitudes are 100% observed. On the contrary, very small objects, very high, will never be observed. But there are some objects in the middle which have a probability of detection which is, let's say, 70%, the yellow curve. Can we detect those objects? Yeah, we can detect them. Sometimes we see them. Can we catalog them? That depends. We do not need only to detect the objects, to observe them once. We need to observe them regularly so we can compute an orbit. An orbit compute today will not be valid 1 week later because we need to propagate them. There are some uncertainties. The uncertainties will grow a lot, and that orbit will not be reliable any longer. We need to observe them regularly. And additionally, we need to observe them as often as possible in order to compute an accurate orbit. So these orbits are those that Holger has mentioned this morning. They are sometimes observed, but I cannot correlate them back because I'm not sure about what was their orbit. Another issue with radar, which I have tried to define in this plot. If you imagine this is the Earth, this is where the radar is, and this is the field of regard, the part of the sky that the radar is trying to catch. Imagine you have a very low orbit with a low inclination. You are out of the field of regard. If the orbit is a little bit higher, then maybe you can cross the field of view of the sensor. But it's very difficult if we are not at a very low latitude to catch the very low and the very low inclined orbits. This is summarized in these plots. We have tried to put for different object size. This is a very small objects from 5 centimeters to 7 centimeters in a simulation exercise. And this is the larger ones from 50 centimeters to 70. The number of simulated objects, which is the red bars, and the observed orbit. This is a function of the objects as a function of the inclination and the perigee. As I said before, it's very difficult, even the larger objects, to be observed if they are in a very low inclined orbit. So we cannot see everything. There is always some remaining risk of having something undetected. Again, as I said before, it's more difficult to observe those lower objects if they are especially related to very low inclinations. That's why even large objects are not observed, although they are very close. One can think, okay, if I come back, if I think about this, okay, that object's 50 centimeters at 400 kilometer distance, I shall observe it. But I have to take into account also the geometrical condition. So what happened with the optical sensors? As we said before, optical sensor can do the job in the higher part of the orbits. Second equation in the talk, I think is the last one. The signal we receive, the signal to noise ratio, depends on the second power of the distance. So we can reach higher altitudes. But there are large but in the optical observation techniques. First, as I mentioned before, if there are clouds, we are seeing nothing. We can only work while the station is at night. Nobody has operated a telescope at daytime, as far as I know. And we need the object to be illuminated. We are not sending any signal to the object that is coming back so we can measure it. We rely on the light coming from the sun. So we try normally to maximize the return light so we can observe even small objects. And the only way to do that is to minimize this phase angle. The smaller the angle is, the larger the amount of light we received. The smaller is 0, of course, but I normally do not point towards the shadow of the Earth. If you imagine this is the sun, this is the Earth, I start observing when the station is here. As the night passes, I'm here, I stop the observations. So we try to observe one part of the, let's imagine this is the geo ring, one part of the geo ring, which is illuminated by the sun, but we do not go to observe this part of the sky. There is another issue which makes difficult the observation with optical telescopes, is that we have a tiny field of view. We have tried to show you something here like this. If you imagine how large is the sky, and you have to cover all the sky with 2 by 2 degrees field of view, it takes time. Fortunately, we know that the geo ring, which is the main orbital regime to be observed with optical sensors, is constrained, let's say, about plus minus 20 degrees. So we do not need, and we normally do not cover the whole sky, but still trying to cover this plus minus 20 degrees takes time. So we need to be very patient, covering all the sky in order to observe the objects. There is another issue which I wouldn't say makes things more complicated, but make things more expensive, is that this is a very stupid plot trying to show that a geo object will always remain over the same sensor site. There's no way with this sensor site that I observe an object here because of the definition of geostationary orbit. It's not more difficult, but it's more expensive. I need to locate at least 4 sensor sites in order to cover the complete geo ring. That's why I mentioned before, it's not that common to have cataloging systems. You have to spend a lot of money to set up the sensors, to do the operations for catalog built up. So we have seen that at least we can do the job with 4 stations, thinking that more or less every station covers 1/4 of the geo ring. There are plenty of observation techniques. Most of them are based on having more than 1 sensor per site. We are going to see it afterwards, and it has the relationship with what I have said before, is that we need very frequent observations in order to compute the orbits accurately. So there are some observation techniques. I have only described one here. Not to observe, I'm coming back, not to observe only this piece of the sky, trying to catch all the objects coming through it, but trying to observe different stripes. So I catch the object when it passes through here, and I catch the object again when it passes through here. So I have double the number of observations, and I can improve the orbit. That's what it's trying to be summarized here. There's another issue about observation techniques. I'm sorry, radars are almost available to military teams, not to civil teams, so I do not have any real data for radar, but I do have for optical sensor. This image is provided by Jaime Nomen, who explained yesterday how the observations are done in order to detect the objects. I don't know if you have ever handled with this, but for somebody who has never taken a look to the telescopes observing space debris, may think that we are observing this. This is not what we observe with a sensor, with a telescope. This is observed by radar, and that helps for attitude determination. What we observed is that. So it becomes a little bit difficult to try to get an object from that. I think you got one, but there are a lot of objects. These are a sequence of 3 images. So if something moves, it's an object, it's not a star. There is one over there. There is one over there. There are more. I think only Jaime can spot all the objects that are... No? Okay. But you can see it's not easy at all. It's quite difficult to observe the sky and catch where the objects are, because we have to differentiate from the background star field. So assuming we have done that job, and we have got that there are some objects over there, we need to compute orbits out of there. In the plot before, in the image before, there were some spots that were clearly visible, but there were others that cannot be observed by the naked eye. But the software somehow can do that. The software processing images can even differentiate between 2 objects that are really there. I don't know if you can observe that. Here we see one. It looks like a trail, but indeed there are 2 objects there. So it's not that easy to get an image and compute where there is an object or there is not an object. There is a huge amount of work behind. As I said before, I'm going to list which are the main challenge, which are the main technologies, but we are not going to go into the details on how this is done. Another special case is faint objects. Okay, there is an object there, but it's quite difficult to catch that there is an object. There are a lot of work to identify objects within an image, and in the same way within the radar signal. Only one slide on a space-based telescope. Is not that normal to use them. There has been some missions flying and providing observations from sky. There are some benefits, as we said before. We never have clouds. You can skip the night operations. You can operate almost continuously if you choose the orbit properly. Contrary to the on ground, also on ground, but in space, where you put the sensor plays a major role. There are several techniques. I have tried to plot here. Just imagine this is the equatorial plane, so we have the geo ring in green, and you can imagine a somehow sun-synchronous orbit, which is the spacecraft is going inside the screen and coming out. It could point against the sun, again, as we have talked before, minimizing the phase angle, trying to increase the light we receive from the object. So it could work for observing the geo ring, similarly to it is done from space. Many people say, okay, it's not worth it to put a sensor here in space, because if I go a little bit closer to the geo ring, I could observe objects that are much smaller, which would be this case. If you imagine an orbit which is close to the geo ring, maybe I'm able to observe 10-centimeter objects, or even I can do imaging. You talked this morning about, is it possible to image objects in order to characterize them from space? As I said before, it's not only important to observe objects, it's also important how frequent, how often I observe them. In this particular case, as this synodic period between the 2 orbits is very large, we observe the objects. I have tried to plot the tracks, the time, the duration for the observation of every single object. Let's have a look to this yellow object. this yellow track. We are observing the object for a long time. So we could obtain a very good orbit, but it's not that good because the geometry is not making us life easy. But the point is that the revisit time is very large. And this kind of observation strategy so close does not allow to compute or to regularly update the catalog to have accurate orbits. So apparently it looks like a good idea, but it's not perfect, as always. Of course, you can imagine thousands of different orbits. For example, okay, I want to go close, but I want to have more, a better revisit frequency. Let's try a GTO. Can play with almost any orbit. Everything has benefits and drawbacks. And this is all about the different sensor types. Just to finish the observation part, it's not only the sensor type you use, it's the way you use it. There is a huge difference between doing tracking and survey, which are the two main techniques we use for building a catalog. Tracking is tracking. I know more or less where the object is, and I try to observe it again. And with this observation, I can improve my a priori knowledge of the orbit. On the contrary, survey try to observe a part of the sky, catch every object is passing through the field of view, and compute an orbit. Of course, identifying which object it is not that easy. As we have seen before, we are not seeing the shape of the object. Okay, that looks like Envisat. No, we are seeing a tiny point which says nothing about who is the object. So the first step when we do survey is what we call correlation. In other fields like asteroid detection, is normally called identification. Is to match the observations we are getting from the sensor to the object the observations belong to. We are going to talk a bit about this technique we use for correlation. The other technique, which is quite important, is what we call initial orbit determination or preliminary orbit determination. The first time I observe an object and I realize it does not correspond to any of the objects I have in my catalog, I have to do something with that observation in order to be able to compute a rough orbit that I can improve afterwards. And afterwards, when I again observe the objects, I use this a priori estimation to refine it, to improve it. In the same way I would do with tracking observations. I have the a priori information and try to improve a bit. So the first step, as this is common to tracking and survey, the first step is correlation, and we will go through these three techniques. Correlation. Okay, one can think, okay, there's one object passing, I go through my catalog, oh, that has a similar orbit. It's not that easy as that because operators tend to use the useful orbital regimes like GEO are all together, or they used to launch very close satellites. This is a real image, again generated by Jaime, where we can see there are several objects here, here. So how you distinguish between those observations? Can you confirm that they belong to one object or to the neighbor? It's not that easy. So these are three techniques that are normally used for correlation purposes. Of course, when I receive an observation, I can try to compute a rough orbit and check which are the orbits that look like it. The other option is to compare this observation with the observation the objects in my catalog should have at that time. That's what I call correlation by observation compatibility. Or another technique, which is also normally used in the asteroid field, is I try to make an orbit determination computation with the new observation and the former observations of the same all the objects in order to check which of the objects corresponds or mathematically provides a better orbit. Again, think about the number of objects we have in the catalog. It's like 15,000 objects. It takes time. Whenever you receive an observation, it takes time to check whether you do it through the orbit comparison, the measurements comparison, or the orbit compatibility. It takes time. Of course, you can filter a lot. If I'm working in the optical field, I know I'm observing MEO or GEO objects. I will never check my observation against LEO, and that helps a lot. So filtering is obviously always done, but even in that case, there are some drawbacks for the different options. When one person sees there are several options, say, okay, you can try one, then if it doesn't work, just try the other. Having a lot of options does not ensure that you will find finally the answer. There are always drawbacks. For example, in the comparison of orbits, if I compute the rough orbit from single observation, the error, I have tried to plot the uncertainty. I don't know if you are used to work with the covariance uncertainty representation. It tried to give you the error you are committing when you compute an orbit. So you do not know if the object is here or here. At least it's inside your covariance, your ellipsoid. This ellipsoid, the size of the error you have from a very small observation track is very large. So if I try to compare the orbit I have just compute with all the objects I have in the catalog, I have to give some threshold because my orbit is so poor accurate that will never fit if my thresholds are very tight. But if I put a very large threshold, you can imagine that an orbit which just pass through this will fall in the threshold. So I will make a lot of miscorrelation. If we go to the case of comparing the observations, I'm not computing an orbit from a very short track, so I'm using the orbit I had before, which is supposed to be more accurate, so I could reduce this threshold and I will not make so many. 5 minutes? Oh my. Okay. Again, there are plenty of techniques. I will skip a bit some of the slides. If we compute and try to compare the observations, we spend many time because for every object in the catalog, I need to compute the estimated observation in order to check if they fit. That's an image I like a lot about the expected observation, which is the green lines, and the real observations I'm receiving from a real sensor. This is real data. If I use a catalog generated the day before, the objects are accurate and they can match pretty well. For example, here, there is no doubt that these observations belong to that object. But if I use an older catalog, just 5 days old catalog, this is using 2-line elements, the predicted observations are very bad. It's not that easy to catch or to match the observations with the expected observation. The other option is just make the orbit determination with all the objects and check which fit better, but this takes a lot of time. There are plenty of mathematical approaches, quite interesting, but that will require an enormous amount of equations, and I have promised not to put many equations in the presentation. So there are plenty of work, plenty of research done here, trying to match observations with the observable maps. These are examples for a correlation we have done in the past with optical sensors. Yes, only a brief description of what this plot means is as I receive observations, I try to assign the observations to every single object. The easy case is the first observation you get. You have nothing in your catalog, so it's object number 1. No error for sure. And as you receive observations, you assign them to the objects. If the observation match with one of the objects you have, I count one track to that object. That's why during the first night, which are the red points, we have the first objects observed, let's say about 70. And as the night passes, so change colors, we are accumulating tracks to every single object. So correlation works somehow, but it has some tricky issues that are summarized at the end. There are always errors. We have to handle with the errors, and we have to encounter the mean to solve them. I will skip this because there's only 2 minutes, no? Initial orbit determination, as I said before, if I try to compute the orbit with a very short observation track, it's pretty difficult. I have tried to show how difficult it is by this stupid plot. If you have a long arc, you have observations covering a large part of the orbit. It's quite easy to say which is the orbit they form. But imagine that the observations are that close. I can compute that orbit, and I can compute that one, but I cannot ensure if the object is following the blue or the red path. Both are correct if I only see the observation I have. So the uncertainty of the object I have is very large. I will skip that part. For example, in the case of geo objects, we have tried to plot here. If I observe one object, and I try to plot also which is the field of view of the sensor I'm using, and I have to catch that object 2 hours after that, probably as the orbit is very bad compute, the object will skip through my field of view. I will never be able to observe them. Okay, I will observe some of them because I'm lucky. I get the good orbit, but it's not always the case. And for GEO, it's somehow a bit easy, but this is the case for GTO. Here, we have 2 hours and a half, but in the GTO case, this is half an hour. If you do not follow up the object half an hour after you have computed the rough orbit, you will never find it again. And that makes a lot of correlation errors if you do not have good orbits. Following step after initial orbit determination is routine orbit determination, how to improve the orbit once you have an a priori estimation. I will skip all these images. The intention is, the objective is to reduce the uncertainty. Whenever you observe, you can reduce the uncertainty of the position of the objects and the velocity, but you can also estimate the area, the mass, or the coefficients for drag or for solar radiation pressure. And we need to estimate also those coefficients in order to be able to propagate somehow accurately the orbits in the future in order to compute their further correlation, their further observations, opportunities, and the risk they pose. I will split that. Okay, so just 2 minutes for talking about difficulties we need to manage. As I said before, errors in correlations occur. It's impossible to avoid them. We need to handle with some thresholds so you can correlate them and accounting for the orbital uncertainties, but that make rooms for errors. In the example I have shown you before, as I do it very quickly, probably you have not noticed that there are objects that are pretty good observed. Every night I have a lot of observation of this object. Second night I have a large number of observations. And the 5th night, I do not have observation of that object. That's strange because it looks like a big object. It has a lot of observations, and it has disappeared from the sky. I doubt it. We have tried to map our catalog of objects we generate from an observation campaign lasting for 9 days with the two-line element objects. And when we try to do that match, we realize that there are a lot of objects that for our 8 nights observations are always matching with the same TLE object. But there are objects that are only matching 7 nights. Of course, if the objects have been observed the first night, which are the red ones, That means that I have observed them till the last night, but not the very last night. Or I have observed it, but I have not been able to correlate. So having a look to those objects, where the problem of those objects are, we realize that there are maneuvers in space. And when you are trying to correlate, you are not assuming maneuvers, you are assuming that the objects go through the perturbations and the Keplerian and perturbed orbits, but you cannot handle with all the maneuvering options, otherwise you will never try to be able to correlate. So one of those objects that are disappearing from the catalog was this case, a maneuver object that we know there were a maneuver at that time. We are pretty sure because the operator confirmed that. I have tried to plot here our identification of the objects and the two-line element identification. Just for you to take attention that this object in the middle is always mapped to the very same object in our catalog. But the last night, we are saying, okay, that object, a pretty well-known satellite, is not your object 7 any longer, which was created the very first night, but is an object created in the 6th night. Oh, that's strange. If we have a look to the distance between the object published in the two-line element and our orbit and the compute orbit, we see that the distance is on the order of magnitude of the error we assume to have in the two-line elements. So our orbit corresponds to the two-line element orbit by 4 kilometers distance. There are a couple of days where the distance doesn't vary. Why? Because the orbit in our catalog is not updated. We are not observing the object any longer. But the orbit in the two-line elements is not updated. They have not correlated the maneuver objects to the old objects. They are waiting to have a little bit more information of that new object that has appeared in the catalog in order to be able to correlate. And that happened also to us. We have a new object, which, if we compare it to the two-line elements, is very far away. It's, 20 kilometers far away. Doesn't look like the same. But as the Americans realize that the object has maneuvered and improved the orbit in the two-line elements, then that orbit looks like ours. So a bit of examples of how maneuvers can be detected, but it has to be done, the job, both in the correlation step and in the orbit determination step. You need to identify that a maneuver has occurred and then that to estimate the maneuver. More difficult is just to finish, is I have just put an example of impulsive maneuvers, which, something that you can manage. But think about low thrust maneuver. Low thrust maneuver can mimic like a perturbation. Just imagine a maneuver in a long track direction. I do not know that the object is maneuvering, but I can just estimate that his area is much larger or much smaller as it is in reality, because I see that I need an along track force in order to fit the orbit. Of course, when the thrust is switched off, the estimation filters should reduce the area or should enlarge it, and objects in space do not do that. So it's a difficulty to handle in the correlation and in the orbit determination steps with low thrust maneuvers. As Holger said this morning, large area to mass ratio objects create problems because we have a lot of uncertainty in the drag and in the solar radiation pressure forces. And for those large area to mass ratio objects, these forces are very much dominant. Attitude determination is an issue. If we do not have know the attitude of the object, and we normally do not have, they are not collaborative objects. We do not know the area, so we cannot estimate very well the orbits. Just to summarize, remember the comic, the plots. Space debris is not a joke, and building a catalog, which is granted somehow, makes or it's a bit difficult, and there are field for researchers to go into it to look.
Okay, let's try to have a couple of questions. If Piyush, let's see if it's here. We can hand it over.
But maybe I can take this one. No, we can share this one.
It's here.
Yeah.
Thank you. Great talk. This was truly educational for me. I have no background in tracking.
I'm happy then.
I'm happy. I'm looking to get into it, but this was truly educational for me. Just wanted to know your thoughts. So a couple things. With the new constellations proposed and launched, I can only presume that can be a nightmare for tracking, especially tracking, maybe not surveying, but tracking. I think that's going to be a big nightmare. And with the new constellations coming up, do we currently possess the resources to do the tracking for these objects?
No, I do not think so. We do not, at least in Europe, we do not have such tracking capabilities, not in space. Holger knows better than me, probably, about the current capabilities. But with that huge number of objects we are talking about, tracking is not possible to be followed.
So according to you, what would we need? What more resources would we need in order to be able to do that?
Improve surveillance sensors, from my point of view. But improving the surveillance sensor has to be accompanied by improving the correlation and the orbit determination techniques. Because if we have plenty more objects, we need to sort out many problems we encounter with correlation. It's not only that putting more sensors, more power to our radars that they can observe smaller objects. We need to handle with all those observations afterwards.
So doing the observation smartly and doing better correlation for the objects.
I think there should be more advances, more research on all the chain, observation, correlation, even orbit determination. I do not think this can be done through tracking if we have 2,000 new objects tracking every day.
Okay,
but that's my personal opinion.
Yeah. Like I said, it is educational for me, so thank you.
Yeah, just a question. Probably you said it at the beginning. Is there really an intention of European countries to match the US Stratcom capabilities? Because I don't have anything against US, but we are basically just relying on. No, it's the same as with GPS. So we're switching to Galileo because we are trying to rely on our own resources. So is there, to your knowledge, I don't know, I have no idea really. I'm not into the topic, so just asking.
I think this is the intention. It's not easy. As I mentioned before, it's very expensive. Collaboration, from my point of view, is the only way to do that. But we have to take into account, maybe Holger, you can also comment, is there is a lot of dual use on these technologies. And many countries do not want to share information, because if you can observe objects in space, you can observe military objects in space. So it's not easy to find the collaboration ways. But if we do not find them, there will be no way to get an European SST system. If this European SST system, whether run by ESA or run by the Commission or run by a group of countries, whether this system will match American performances will need time. For sure, it will not be in one day. It will not be in 1 year, but we shall start. No matter if the performances are not that good, we will get to that. And probably in the future, if we start now, we can even collaborate with the Americans and do something together. As I said, for me, collaboration is the only way. But I know this is a naive way of thinking. It's not easy. Dual technology make problems, but it was the same case for GPS, I guess. Yeah.
The United States expressed a wish to be independent, or they said autonomous, to use the right word, autonomous, but as Noelia said, collaborative. So not excluding collaboration,
it makes sense to look at, also complementary design. So, for example, where the Americans have weaknesses in lower latitudes or in geo, that we are better there, and possibly avoid duplications in other fields. That makes a lot of sense. But at the moment, budget-wise, we are far away from rivaling, at least,
Yeah.
There is enormous steps to be taken at the moment that we reach even a comparable level. We are far away from that.
But if we do not start, we will never get that.
There is a good exchange, I must say, every time where there's an imminent re-entry of a risk object, we have a perfect collaboration and exchange of measurements across worldwide, I must say, including Russian sensors, including American sensors, because that's where you want good coverage, frequent observations to get an accurate prediction, and that works. But these are special cases, and we are far away from continuous surveillance of 17,000 objects at the moment. We are the junior partner there. Yeah.
But I think we are closer than we were 20 years ago.
Oh yes.
So still there are some hopes.
I would ask, once we are getting to the time for the roundtable, that the questions that are still to be responded, that are already responded by the members of the roundtable. So
keep asking questions.
Noelia, Holger, Andrew, please come here.